Picture this. A cosmic detective. Not just, looking for visual clues out there in space,
Right.
but actually feeling the ripples, the actual undulations of space-time itself. It sounds a bit like science fiction, doesn't it?
It really does. But today, we're taking a deep dive into how a truly groundbreaking mission, the European Space Agency's Gaia, is helping make that cosmic detection, well, a reality.
Gaia.
Oh, yeah.
Yeah.
You probably know Gaia for its amazing precision in mapping our galaxy, the Milky Way.
Oh, yeah, the star mapper.
Exactly. But we're going to unpack its surprising and actually quite profound contributions to this really cutting-edge field of gravitational wave research.
Huh.
So think of this as your shortcut, a way to understand how this one mission is helping us hear the universe in a completely new way.
Hear the universe. I like that. Okay, so let's set the stage a bit. Maybe a quick refresher on gravitational waves themselves.
Good idea.
Simply put, they're ripples
Yeah.
in the fabric of space-time itself,
Mm.
generated by, well, accelerating masses. Things like two massive objects spiraling into each other, maybe black holes or neutron stars.
Exactly. And Einstein, of course, predicted them way back in 1916, part of his general theory of relativity.
But for decades, the evidence was just indirect.
That's right, indirect. The most famous case was probably the Hulse-Taylor binary pulsar back in 1974.
Right.
Its orbit was seen to be decaying, shrinking, exactly as you'd predict if it was losing energy by sending out these gravitational ripples. It was, well, a powerful hint, a cosmic whisper, you could say.
A whisper until the roar, 2015. That was the big one.
Absolutely. LIGO. The detectors in the U.S. made the first direct observation.
Incredible.
They picked up a signal from two merging black holes, and just like that, bang, the universe had a whole new way to talk to us.
And that's where Gaia comes in ways maybe we wouldn't expect.
Precisely. Its role is turning out to be, well, invaluable in this whole gravitational wave hunt. So in this deep dive, we'll look at three really fascinating areas where Gaia is making a huge difference.
Lay them out for us.
Okay. First, helping identify these special verification binaries for the upcoming LISA mission.
LISA, right, the space-based detector.
Second, helping in the crucial search for those elusive flashes of light electromagnetic counterparts that sometimes go along with gravitational wave events.
Ah, the multi-messenger aspect.
Exactly. And third, providing vital clues, constraints really, on the faint, ancient hum of gravity waves echoing from the early universe, the stochastic background.
Okay, lots to unpack there. Let's start with that first one. Gaia and LISA's verification binaries.
Right.
Now, LISA Laser Interferometer Space Antenna. Big future space mission, designed specifically for gravitational waves. Tell us more.
Yeah, Lisa, it's been a long time coming. Its roots go way back, concepts from the 80s even.
Wow, really?
Yeah, it shows you how important people thought this was even then. It was proposed to ESA in 83, identified as a cornerstone mission in 95, and now, well, the current launch target is around 2038.
2038. Okay, still a ways off, but getting closer.
Yeah.
China has something similar too, right? Tianjin.
That's right, Tianjin. Similar timescale, and when Lisa gets up there, it's going to be targeting some truly spectacular sources.
Like what?
Things like compact neutron star black hole binaries spiraling together, massive black hole binaries in the hearts of galaxies, these weird things called extreme mass ratio in spirals.
Where something small spirals into something huge.
Exactly. And also a huge population of compact white dwarf binaries, double white dwarfs orbiting each other closely.
Right, you mentioned that population is enormous, like maybe 10 million of them, all emitting gravitational waves.
That's the estimate, yeah. 10 million, maybe more. All emitting waves across this very low frequency band that Lisa is designed for. Frequencies from 10 to the -1 down to 10 to the -5 hertz, way lower than LIGO can hear.
And most of those signals will just blur together, creating a kind of background noise.
Exactly. That's what we call the stochastic gravitational wave foreground, a confusion noise from all those galactic binaries. But amongst that, LISA expects to pick out thousands individually.
So how did these verification binaries fit in? Are they different?
They are. They're kind of special cases. Before Gaia really got going, we knew of about maybe 25 short-period compact white dwarf binaries.
Short period meaning orbiting really fast.
Yeah, periods of just a few hours. And these were considered guaranteed LISA sources. Known signals. These are our verification binaries.
The ones they can test the system with. like calibration targets.
That's a great way to put it. Calibration targets. LISA expects to resolve maybe 1,000 to 10,000 of these types of binaries overall. The verification ones are just the ones we already know about before launch. Their signals are pretty clean, long-lived, almost a single tone, just drifting slightly in frequency.
Okay, so they're confirmed targets. LISA can point, figuratively speaking, and say, we should hear something from there at this frequency.
Exactly. Check the instruments are working.
And this is where Gaia comes in and makes things, well, even better.
This is where it gets really interesting. Gaia, by mapping billions of stars with such insane precision, has become absolutely instrumental in finding more of these crucial verification binaries.
How many more are we talking?
Well, it's been a bit of an explosion. Recent work, like papers by Wren and colleagues in 2023, used Gaia data cross-matched with the Zwicky Transient Facility. They found hundreds of short-period white dwarf binaries.
Hundreds.
Yeah. And from those, they identified 6 new definite LISA candidates. Then another study, Kupfer and colleagues also in 2023, used later Gaia data. They updated the whole list. Found 16 new verification binaries detectable after just 3 months of LISA observing, and 21 new ones detectable over 4 years.
Wow, so Gaia has basically tripled the number of known verification binaries.
Pretty much. In just the last few years, we've gone from, about 25 to well over 40, nearly 50 confirmed ones with measurable properties thanks to Gaia distances. It includes different types too, detached double white dwarfs, AMCVN binaries, even an ultra-compact X-ray binary.
So what's the bottom line here? Gaia is essentially drawing LISA a map.
That's a perfect analogy. It's providing a vital roadmap for LISA, making sure that when it launches, it has this really solid list of known targets to, well, verify its detections right from the start.
It's like giving them a confirmed checklist for success before they even leave the ground.
Exactly. It massively boosts the chances of LISA hitting the ground running or hitting the space floating with solid results right away.
That's fantastic. Okay, let's shift gears. Point 2, hunting electromagnetic counterparts with Gaia.
Right. The light that sometimes comes with the waves.
LIGO's detection's amazing. Over 90 now, right? Across their first 3 observing runs, 01, 02, 03. Mostly black hole mergers.
Mostly, yeah. But there's that fascinating distinction you mentioned.
The neutron star merger.
GW 170817. That first binary neutron star merger was different. It wasn't just gravitational waves. We also saw it as a gamma ray burst and this bright optical flash called a kilonova.
Powered by radioactive decay from heavy elements being made.
Exactly. It was huge for this whole idea of multi-messenger astronomy, connecting the gravitational wave universe with the light-based one.
But the challenge is finding that light, isn't it? Gravitational wave detectors, they don't pinpoint sources very well.
Not yet, anyway. They typically narrow it down to a patch of sky, maybe a few hundred square degrees in area. That's huge.
Like trying to find one specific firefly in a massive forest at night from miles away.
Good analogy. It's really tough to scan that much sky quickly enough to catch a fading flash like a kilonova.
And Gaia can help here with its alert system.
That's the idea. Gaia isn't just mapping static positions, it's an all-sky, multi-epoch photometric survey.
Meaning it repeatedly scans the whole sky and measures brightness changes.
Exactly. So it's perfectly built to find sudden flashes of light, things that weren't there before. And researchers, Kostura and colleagues back in 2020 developed an extension to the Gaia Science Alert system specifically for this.
How does it work? Is it faster?
It is. Normally, Gaia needs to see something in both of its fields of view for a secure detection. This extension, though, it triggers an alert based on just one detection of a previously unknown source in a single field of view transit.
Ah, so it lowers the detection threshold to get alerts out faster.
Right. Now, the trade-off, naturally, is you get more false alerts, things that aren't real astronomical flashes.
Makes sense.
But simulations, based on LEGO's O3 run, suggested that maybe 16% or so of gravitational wave events should happen in sky regions that Gaia scans within about 7 days.
Okay.
And this rapid alert system could potentially flag something like 21 candidate flashes per day from the whole sky.
Yep.
The actual implementation of this specific alert mode is still ongoing, but it shows how Gaia is, evolving, adapting to new scientific needs.
And why should you, our listener, care about finding these light flashes, these counterparts?
Well, finding them is absolutely crucial for understanding the physics going on in these extreme cosmic events. Black hole mergers, neutron star collisions.
It gives us more information than just the waves alone.
Tons more. It opens up this whole new era of multi-messenger astronomy. You get the gravitational wave signal, the sound, if you like, and you get the electromagnetic signal, the light. Putting them together gives you a much, much more complete picture of what actually happened.
Like hearing thunder and seeing the lightning.
Oh.
You understand the storm better.
Exactly. It lets us really piece together the full story of these cosmic cataclysms, gives us insights neither waves nor light alone could provide.
Okay, fascinating. Now let's tackle the third piece. Gaia and the stochastic gravitational wave background.
Right, the big one, or rather the very faint one.
We mentioned the stochastic foreground earlier, that confusion noise from all the white dwarf binaries in our galaxy. This background is different.
Totally different, the stochastic gravitational wave background. The theory is it was generated way back in the early universe,
Out.
like really early, maybe during cosmic inflation, fractions of a second after the Big Bang, or perhaps from vibrating cosmic strings, if they exist, or maybe from phase transitions in the early universe, like colliding bubbles when fundamental forces separated.
Wow. So we're talking about echoes from the universe's formation.
That's the idea. Each of these different scenarios predicts a slightly different kind of faint, pervasive hum of gravitational waves filling all of space. A relic signal.
Okay, my mind's slightly blown already.
Yeah.
How on earth could we detect something so faint, so ancient? What's the trick?
Well, the idea is actually pretty clever. It relies on incredibly precise measurements. Imagine gravitational waves from this background constantly washing over us, over our telescopes.
Okay.
A telescope like Gaia, which is essentially in gravitational freefall as it orbits, would be subtly affected. The passing waves would cause a tiny, time-varying shift in the apparent position of any distant star or quasar it's looking at.
So the stars would seem to wobble slightly, not because they are wobbling, but because the space-time the telescope is in is wobbling.
Exactly. We call them spurious proper motions, like looking at distant lights through subtly shimmering air. The apparent positions wiggle around a tiny bit, and the amount of wiggle, the angular displacement, is proportional to the strength of the gravitational wave field passing the telescope.
Okay, that makes sense. It's an effect at the telescope.
And that's key. What's really interesting is that for very distant sources, like the quasars Gaia observes, the effect of the waves passing over the telescope is much, much bigger than any effect way out at the source or along the light's path.
So all the distant things should seem to wobble in a similar, coordinated way.
Yes. It implies these apparent motions would be coherent across the whole sky, like the entire celestial sphere is subtly breathing or flexing in unison due to these ancient waves. The relative motion between two nearby sources would be proportional to how far apart they appear on the sky.
Mind-bending stuff. Have we had any hints of this before?
Well, there have been constraints for years. Limits based on Big Bang nucleosynthesis, how much energy could be in waves without messing up the formation of light elements. Also, limits from radio astronomy, like VLBI astrometry, and tiny irregularities in the timing of millisecond pulsars.
Pulsar timing. I heard something about that recently.
This is where it gets really exciting. Just last year, June 2023, 4 independent groups working with pulsar timing arrays, they all announced the detection of a signal consistent with this stochastic background.
Wow, really? So it's potentially been found.
It looks that way. It's a monumental discovery, a huge confirmation, and it sets the stage for much more detailed study.
And Gaia has a role here, too, in confirming or characterizing this background hum.
Absolutely. From Gaia's early days, scientists realized it could place really useful limits on the energy density of these primordial gravitational waves, especially at very low frequencies.
How does Gaia's data help?
A researcher named Kleiner pointed out back in 2018 there are sort of two regimes. One is where the waves directly influence the calculated proper motions, the apparent sideways movement of stars and quasars. Gaia's best sensitivity here is at super low frequencies, like 1011 to 10 hertz, much lower than pulsars or LISA.
Than the other regime.
The other is where the effects are even more subtle, and they mostly show up in the residuals, the tiny leftover errors or wobbles after you fit the standard model of a star's position and motion.
And are we seeing hints in the Gaia data already?
We are. Some exciting early results. A few studies, Liao and colleagues in 2021 used about 300,000 quasars from an early Gaia data release. They found a hint of what's called a quadrupole anisotropy, a specific pattern across the sky in the quasar parallaxes, which could indicate these waves.
Quasars are key because they're so distant they should be statistically fixed points.
Exactly. Any correlated apparent motion is likely due to something else, like gravitational waves or maybe instrumental effects. Other studies, like Aoyama et al., 2021, and Jeraba et al., 2023, looked at the proper motions of hundreds of thousands of quasars in Gaia, data releases DR3 and EDR3. They derived upper limits on the energy density of the waves, what physicists call omega GW.
So they're putting numbers on it, saying the background hum can't be stronger than this level.
Precisely. They're setting observational constraints. Now, it's important to say these are early days. There are still known systematic effects in the Gaia data that need to be fully understood and accounted for.
Of course, it's incredibly precise work.
Incredibly. But even these early results are really promising. They point towards vastly improved prospects with future Gaia data releases and maybe future missions.
How sensitive could we get?
Well, if this stochastic background is close to the current upper limits from pulsars, it would cause apparent proper motion shifts of maybe 1 nanoarc second per year. Tiny.
Nanoarc second, that's
Yeah.
possibly small.
It is. But it's potentially measurable. And it implies that optical astrometry, building on Gaia's legacy, could potentially get another 2 or 3 orders of magnitude more accurate.
Wow.
Which means nanoarc second astrometry has really excellent prospects for not just detecting, but actually mapping any cosmological gravity wave background in detail, charting the echoes of the Big Bang.
What an incredible journey. So
Yeah.
let's just quickly recap. Gaia, we know it as this amazing star surveyor mapping our galaxy.
Right, building the best 3D map of the Milky Way.
But it's also turning out to be this crucial, maybe unexpected player in the hunt for gravitational waves.
Absolutely. From helping find those specific verification binary systems for LISA,
Giving Lisa that roadmap.
to helping us hunt for the faint flashes of light, the kilonovas, that accompany some of the mergers, LIGO and Virgo C,
The multi-messenger connection.
and even giving us these amazing constraints on the faint ancient hum of gravitational waves from the early universe itself, the stochastic background.
It all comes down to that incredible precision, doesn't it? Measuring tiny shifts in position and movement allows us to probe phenomena as huge and fundamental as the fabric of space-time.
It really does. It's an astrometry mission that has completely transcended its original scientific goals in many ways. Its data is just so rich.
So what does this all mean for you listening in? Well, next time you look up at the night sky, just think. The same mission that's mapping those stars you see.
Or can't see.
Right. That same mission's data might also be helping us hear the echoes of merging black holes halfway across the universe, and maybe even the faint ancient hum from the universe's very first moments. It really makes you wonder, doesn't it?
It does.
What other scientific fields, maybe ones that seem totally unrelated, could get a huge boost from an unexpected deep dive into these incredibly rich data sets we're building?